The Hadoop Professional Certificate course deals with the concept of Hadoop and big data. The architecture of Hadoop is clearly explained and discussed in details with emphasis on HDFS, the Hadoop Distributed File System. The installation of Hadoop clusters is discussed and demonstrated, including essential file system commands. This course explains the MapReduce model in depth to get a solid understanding of the key concepts, including key value pairs and the process of job execution using mappers and reducers. Streaming is an important component of Hadoop, allowing languages other than Java to use the Hadoop MapReduce system, and this course explains it in details. Commands to be used with the Hadoop archive utility are clearly explained and demonstrated. Pig and all its practical commands that go with it are clearly explained. Hive commands are also dealt with in great details. File input and output is explained with exercises and examples using Java programs. This course explains how Scoop is used for export and import of data between MySQL, HDFS, Hive, and HBase.
So the course is called Mastering Hadoop. It's got a lot in it in terms of technicalities, but what we'll do is we'll go step by step. So in today's session, we're going to cover more about what's big data, what's Hadoop, what is its ecosystem, features, what kind of an architecture does Hadoop have. So in case you're not too familiar with it, you'll come to know why do we use Hadoop, what are the good things about it, how is it different from other systems, and generally how are people using it today. So that's about the introduction to this. So we'll start with what is big data, because Hadoop is all about handling big data. So big data is actually a large collection of data. It's also called data sets. So as the name implies, big, which means a huge collection of data. So we are talking about unstructured data mostly when we say big data, because in the traditional databases, if you've dealt with Oracle or SQL Server, those are all databases which are called relational databases. And those databases keep everything in a very structured manner. So you know exactly which column, which table, what's the data type. So that's very structured data. So the structure of the data is predefined. When we say big data, we are actually talking about having data in mostly unstructured and semi-structured data. It's not like big data cannot handle structured data, but since those other technologies fail to handle such kind of unstructured data, Excel spreadsheets, Word documents, PDF files, so big data is one technology which makes you, which enables you to actually handle that kind of data. So we'll talk a little more about it as we go down, but so that's the reason that big data technology is catching up, because there were some limitations with those traditional databases. Now, that's what's mentioned over here. Now, some of these companies like Twitter, Facebook, Yahoo is probably the largest user, and Facebook and Twitter, they use big data technology. They use Hadoop clusters. So typically in a Hadoop cluster, when we say cluster, it's a collection of machines or nodes that process data in parallel, and it increases the speed of processing of data. So especially Twitter, Facebook, all these new applications which are coming up, they need to process data in a massive quantity. So there are thousands and millions of people on their website who post hundreds of comments every day, and then Twitter needs to know, for example, what is people's preferences, what kind of topics are getting more popular, so that they can do some targeted marketing or know more about their customers. Facebook has similar requirements. So essentially, Twitter, Facebook, and all these companies were having a big challenge to process data because it would take days to actually be able to generate reports or some dashboards or draw some meaningful statistics out of the data. So that's how big data came about, and Google came up first with a framework, and that was called that brought about the HDFS system, and it was open source, and they let Apache take over, and Apache came up with this Apache Hadoop system. So it initially actually started with Google. Google had a different name for it, but essentially it was later developed by Apache. So now, so when we talk about volumes of data, you might have already dealt with data which is a few kilobytes, megabytes, or even gigabytes or terabytes. This one goes further. When you talk about big data, we are actually talking about terabytes of data at least, and so it can be this explains like what are the different units we use for big data. You see, so you have 1 terabyte versus a petabyte or an exabyte, a zettabyte, yottabyte, brontobyte, and geobyte. I don't know if the spelling is right or not on the last one. But so these are huge quantities of data, right? So what you have to do is multiply by the factor of 1024 every time, and you keep going higher. So it's very common.
So is it like minimum amount of data if we talk about, is it in gigabytes, right?
Yeah, usually when we go to a Hadoop kind of a platform, people go to it because of the massiveness of their data. So it's not like Hadoop cannot be used for smaller sizes of data. It can be. But usually for those smaller databases, it's sufficient to use the traditional RDBMS systems and all, and you can pretty much do a lot of stuff. Or else you could use it for smaller databases as well. For example, if you were to do some processing on log files or some unstructured data, you would still like to use big data. So, yeah, 1 gigabyte is like 1,000 megabytes. But in most companies which are using big data, there are hundreds of companies which are actually today using it. It has become very popular. If you go to Apache Server Foundation, you can actually see a lot of companies' names, which includes all these examples I gave you: Twitter, Yahoo, Facebook. I think the largest is Yahoo. They have, I don't know, thousands of servers in a cluster. So they use it in a big way. But yeah, so your question was like, is that like a minimum size of 1 gig or something? Is that what your question is, Mac?
Yeah.
Right. So there's no minimum size as such. It can do smaller data as well, but it is typically used for larger quantities of data. It really excels and shines when the data sizes grow. So I just wanted that you be aware of these different terms like gigabyte, terabyte, because when you start dealing with big data technology, people are going to talk in these terms. Like if you were to join Yahoo or something, and the data grows pretty huge, so they might say, you've got 1 exabyte of data. Now you might get a blank to what is 1 exabyte? Come on, okay, fine. It means 1,000 petabytes. Right? So, just wanted to make sure that we are aware of some units. Now, so data grows astronomically. The reason that data is growing today and why is it that big data is gaining popularity, over the recent years, over the last 10 years or so, all of a sudden there's been an explosion of data coming from different sources. It's no longer just, some maybe mainframe computers or mini computers holding data. Today, data sources have grown. Earlier we never used to have data being analyzed coming from cell phones, right? Today people use emails on cell phones, they chat, they do everything, WhatsApp and everything, right? So all this is creating data. So there's a huge explosion in data. There's astronomically growing. It's exponential in growth. There's internet, mobile devices, readers, sensors. All of these are used tremendously now to gain insight into what's going on, right, on different systems, different functions. So as a result, this data has exploded tremendously. So there are some examples over here about huge data sizes. So large companies typically have found that it's getting immensely difficult for them to keep on using the traditional data sources. Like, for example, if you had an Oracle database of 1 terabyte size, it will come down to its knees if you were to actually do something like a, a count of all the records in a table which is stored in that 1 terabyte. Like, so let's say it has several millions of records. So it will take like maybe an hour to return back a result in a query. So to meet that challenge, big data came about. It introduces parallel processing. It introduces some concepts which help you analyze data more quickly. So you cannot today think of doing analytics on Oracle kind of databases when they grow to a huge size, like for banks or for companies which have like hundreds of terabytes of data. So if they were to run a query, like an SQL query, to fetch back information that produces a report, it's just almost impossible. What they would have to do is, they will do something like a nightly batch. It will collect data in some other database, and then a report would run on it. So, it introduces all these delays in actually being able to generate meaningful statistics out of data. That's where big data now is helping in, overcoming that challenge. So when we talk about big data, one common thing that people say is volume, velocity, and variety. So it should be able to handle a lot of volume, and that's what big data helps with, like we said. Velocity is like at the speed at which data comes in, right? So today, like for example, when a Boeing 787 flight is en route, it sends something like an average of 500 gigabytes of data in a single flight. So now that's a huge amount of data. So if they were to collect all that data together and analyze it, it would be a challenge with traditional data, right? So, and it's coming at a pretty fast speed because it's coming through sensors, which are embedded in the airplane. It gives you, information about what's the engine temperature or, what's the speed of the aircraft and, things of that nature through sensors. Variety is again like different types of data. So, you've got spreadsheets, text, image data, geolocations, logs, sensor data. So there's a huge amount of different types of data. And there's no single platform that can actually analyze that data of different types. So the idea is to start using some technology like Hadoop to be able to manage different types of data. Okay, I'll take a little pause here. Do you have any questions at this point?
No, I don't have any question, but I think we lost Hekel. I couldn't see her.
What's that?
Is there on the call? Hekel is there on the call?
Oh.
Yes, I'm there.
Okay, fine.
Okay,
Right.
okay.
You're able to see everything, Hekel?
Yeah.
Okay, good. So now we'll talk about, having talked about big data, we come to what's Hadoop. So Hadoop is an open source framework for writing and running distributed applications that process large amounts of data. So there are several things in this small definition. One is that it's open source, which makes it, freely available. There's no cost to actually using it. The second thing you note over here is it's a framework, right? So it's not like any particular technology or a tool. It's more like a framework. It gives you a way of doing, of processing data, of doing some things using different technologies. So it's open source framework. Running and writing distributed applications. So distributed applications is another term that's used here. So when we say distributed applications, it means what? It means it allows you to run applications in a distributed fashion, which means your servers which are holding your data could be across multiple locations in different places. Your applications which are interacting with that data could be more than one and need to interact with each other. So it distributes processing loads across different applications. Okay? And it processes large amounts of data. So that's why it's suitable for big data. And there are two very important components of Hadoop. One's MapReduce, and the other is HDFS. Okay. We'll talk about this as we go forward.
Yes, yes. Yeah.
Okay. Now, so any questions so far?
No.
Okay.
No.
Right. So this is further explaining what Hadoop is, a little bit about its history. It's an open source project. Apache Server Foundation actually owns it. There was a person called Doug Cutting, and he used Java and named to develop this Hadoop system, and essentially he named it after his son's toy elephant. He bought a toy elephant, a yellow-colored elephant, and he asked his son, "What do you want to call the elephant?" And the son said, "Hadoop." Kids don't have any, preconceived notions about anything, so it sounded pretty creative to him. Call it Hadoop. There's nothing called Hadoop otherwise. So interesting.
Yeah, so mainly that means it's written in Java, is it?
Yes, it's written in Java. Good for you, right? You're a Java teacher. Yeah, it's written in Java. It uses a lot of Java.
So even if we want to use Python in Hadoop, then we have to use some kind of interface in between, is it?
If you use Python, so as we go forward, you'll see that when you use Hadoop, you use this MapReduce framework. So what happens in MapReduce is, that's why it's more a framework, they say, than a tool or a technology. So it doesn't bind you to specifically using Python. When you do MapReduce,
Yeah.
You write some programs, and you could be using Python for it, or you could use Ruby,
Any other language,
or
yeah.
Java or C++, several different languages, object-oriented. Okay?
Okay.
All right, then.
No, but my question is like, if I don't use Java, rather than if I use any other language,
yes.
So is there needs to be some framework or some interface to connect to Hadoop, that language? Or it works fine without using anything in between to connect to, I don't know.
Yeah.
What am I...
Exactly. You'll come to know as we go forward. Because there are several things that you learn on how you're going to use those Java programs or Ruby programs or Python programs in Hadoop. We'll see it in a while. But
Okay.
But yes, there are some little interface available to monitor what's going on in Hadoop, but it's mostly all backend operations. So you do need to know something about Unix, for example, because it's basically built on Linux. And if you were to run it on Windows, you would have to configure Windows for a Unix-like environment. So there's a utility called Cygwin, which you have to download and install on your Windows machine. And then it can start taking Unix commands. So yeah, there's going to be a lot of work more on the Unix side. So it's but it's a good question, right? So there's no interfaces have been built by the user community thereafter. So there are tools which have been built on top of what Hadoop offers. So Hadoop is really more about this MapReduce, tool or framework, and apart from that, it's more about HDFS, which is a file system. Just like if you had a file system like DOS or Windows or Unix, right? They by themselves, Unix, for example, doesn't come with any specific interface. You just go there, you just log in, you're at the shell prompt, and you pretty much run your commands from the command prompt. There are GUI interfaces that have been built on top of it by the user communities, but you could very well work without those as well. So it's something similar. As it's evolving, people are developing some interfaces around it to make it easier to manage and to do their work. But the core, components don't come with something like you would have in an application. That's why it's not an application. Hadoop is more a framework. But yeah, we'll see more as we go forward. It'll become clearer.
Okay.
Okay, so it's all about data, databases, nodes and clusters, a lot about how you administer your jobs that run on different nodes, that kind of stuff. It's very different from writing, Python or Ruby or Java programs. So it's going to be a little different kind of an experience for you. So they say, what is it not? So it is not an OLTP system. You know what's an OLTP system? So an OLTP system is online transaction processing.
Transaction processing systems, maybe.
Correct. So what an OLTP system does is it's online, right? There are two things, online and transactional, which means you send transactions on the fly. As you're working, everything is done in real time. So you post transactions, like for example, in a banking application, you might be depositing something from your cell phone or over the internet, or you might be taking cash out from an ATM, and everything is going through the database and getting stored there. Transactions are happening very quickly. That kind of a system is an online transaction processing system. Now, this Hadoop is not an alternative to it, which means when you talk Hadoop, you don't build it for an online transaction processing. This is more for analysis of data. So, you basically have more batch-orientedness in this, meaning the data is already collected somewhere, and then you run your programs to analyze the data, or you do some processing on that data. That's what Hadoop is for. It's not an online transaction processing system. Okay? It's not an OLAP system. OLAP is online analytical processing system. So it's not like the traditional tools that you have, if you've heard of ClickView or some tools like Business Objects. And also those tools help you to analyze data, and they usually run through queries, like they would work on SQL queries. Whereas Hadoop does not require SQL queries. It can work without that. So there's a different way of accessing data in Hadoop. It's not a replacement of an RDBMS like Oracle and DB2. It doesn't mean that Oracle should get outdated or DB2 should be replaced with something like an HDFS or a Hadoop system. It is not a substitute. It doesn't replace it. It works differently. It solves different business challenges. Okay. It's not suitable for sequential access of data, and it works in a batch operation, which means this is pretty self-explanatory. Like I said, you collect data, then you run batch programs on it. It's not like something which does a random access of data as you're working on an application. So like you see in the note, it complements these other systems, OLTP, OLAP, RDBMS and all, but it's not a replacement for them. Now we're just talking, it's good to also know that Hadoop is an ecosystem. There are many open source tools and technologies available that work with Hadoop. Like there's something called Lucene, which is a Java-based indexing and search technology. There's something called Solar, which is a search server. Then there are multiple products which actually work well with Hadoop, and a few of them have been mentioned over here. Some of the more common ones. PyLucene is a Python extension for accessing Java Lucene. So Java Lucene is another product from Apache Server Foundation, and there's a link given over here. If you're interested, you could visit that. HBase or HDFS actually should have been there is a Hadoop database. HBase itself is an open source distributed database called a NoSQL database. I don't think we are covering that in this course, but we might talk about it a little more as we go forward. So HBase has like big data, like table-like capabilities. It sits on top of Hadoop and HDFS. So if you were to use this, it allows you to further, analyze data quickly from Hadoop. So there's more examples on
So, is it like Hadoop maintains its own database or something?
Yeah, Hadoop,
HDFS?
as we will see very soon, it has its own file system. So if you had Unix files or any system files, you would they would reside on your somewhere on your local operating system. But Hadoop
Yeah.
has its own separate file system that sits on top of that, right? So that's the way it's been built. So in order to access files in Hadoop, you will have some specific commands that Hadoop provides to be able to, write data, to read data, and to see what files are lying in the system and all that. So there are some specific.
Yeah. We first have to enter to HDFS, then only we can access it.
Yes, yeah. You need to start some processes, Hadoop processes. Once you do that, then if you want to see Hadoop data, Hadoop files, then there are specific commands for it. Right.
Okay.
This here is a little example of what's going on now in the industry. So, companies have, with this new technology coming, extra Hadoop cluster layer has been added, so a lot of companies are now doing this, which means traditionally they used to have, as you see here on the top, they would have, these kind of applications are very common in every company, like SAS is a statistical analysis tool, R is another statistical open source tool, OpenOffice, PDF readers. There are lots of data mining tools and reports. Everyone has not been mentioned here. Just as an example, I've put in some over here, but these are analytical tools that help you to create reports and be able to analyze data, right? Then there's at the bottom you see there's a structured data layer. Like most companies would have Oracle or DB2, which is an IBM product. They would have some SAS file, some SQL Server database or something. So one or more of these are very commonly seen in companies, right? And then you have this middle layer of Hadoop cluster. So with this thing in the green is all new now, like with Hadoop coming in. So Hadoop comes with one thing, all these different type of data that it can handle. So this here in the middle is the data layer, and data can be structured, semi-structured, or unstructured. So I've specifically written semi-structured and unstructured only over here and kept structured away because Hadoop would typically be able to solve problems with these two types of data. And all these technologies at the bottom, they are not very good at being able to analyze this kind of data or running queries on them. So now, here on top are the tools, like there's Pig and Hive and HDFS. There are different applications that are in the Hadoop ecosystem, which are used to interact with this data. Okay, so this is kind of like a high-level architecture showing us like how typically tools are positioned in a company today, right? So if you look here, what is an unstructured data? This might be a common question. What is a semi-structured data? An unstructured data, is data which has no structure to it. Like when you have a Word document or something, so you can just write free text in it. There's no structure to it, meaning there's no column level information or data type. You could just do anything you want. Same with emails and audio files and all. Semi-structured data have some kind of a little structure to it. Spreadsheets, for example, right? There would be column A through column J maybe in your spreadsheet. And so it is having some columnar and row kind of a design. But it's still not a fixed structure. Like, one person might use a spreadsheet in one way, another might use it in another way. You can still get data through it, but it's still not fully structured. It's called a semi-structured data, right? It has some structure to it, but not full-blown structure like you would have in Oracle. And then there is structured data, which we already talked about. So these two, structured and unstructured data. And what kind of data is usually there? Like a web log file. And when you have a log file on the web, usually programs are written to write to a log file. And they would typically have data, something like which event happened and was there an error. There might be, a specific column number so-and-so till column number so-and-so. It might have, the reason for the error. Or else it might not have a specific length of the column, but it would have information about which event happened, what error occurred, or some status, etc. Right? So log files, therefore, are semi-structured. They have some structure to it because you know exactly what kind of data they contain and how it's organized, but it's not completely structured. It could be like maybe appearing as just like 5 characters in one row. It might be 100 characters in another one. You haven't defined whether it should be exactly 100 or exactly 5, right? So it's semi-structured. Did you get that concept?
Yeah.
Okay.
Yes.
All right. We'll move on. So there's some more examples about, there's Pig, there's Apache Pig, Jackwell, Zookeeper. So these are all different types of applications which are being used, like JAQL. This is a query language. So this kind of like helps you, people who are more familiar with, SQL query. So Jackwell will help them actually writing some queries of the SQL types to be able to see data which is collected in Hadoop.
I have one question, Shashi.
Yeah.
Yeah. So basically, to access that structured and unstructured database, we will be using these technologies, right? Like Jackwell or Zookeeper or Pig or Hive.
Yeah. Mm-hmm.
So Hadoop is not itself a system or a software or an application that will be used.
Mm-hmm.
Right? That's what it's true, no? Like Hadoop is not a software, like say for a Ruby. Ruby itself is a programming language. So Hadoop is not as such programming language. It's a technology.
Right. It's an open source framework. So it's Hadoop by itself can actually see. We are talking more about using a database or a file system, HDFS. So it uses a file system, right? However, you could use not just HDFS. You could actually also use an IBM file system. So there's another one that IBM uses. I think it's called HDFS or something. I'm forgetting what's its full name. I haven't used it. But so it could actually, Hadoop could use that one as well. It will work with it. It can work with it. So it's not limited to one particular, strict file system also. But HDFS has been designed to support the Hadoop framework. So these languages like Pig and Hive and all, they would work very well if somebody used the framework of Hadoop and created a file system, for example. Right? So these different languages will actually use the file system that we used. So when you're implementing your part of Hadoop, if you've used HDFS, then you might be using Pig and Hive to be able to query the data which is contained in it, or to process the data inside that HDFS file system. Because data, when it's lying in an HDFS file system, it's not like data lying in Oracle where you store data in tables, so you know exactly which table to query and what column to query. In Hadoop, everything is lying in just raw data format in a file system. There's no structure to it. So when you write, so you have to write your own programs to define in which way you want to, process the data, and you kind of like build a structure on the fly. You might say, I want to, that there's a log file lying, and it's got maybe 1 million rows in it. It's got all information about everything, every user that logged into your website at what time, maybe some log file of that kind, right? So in this log file, it's just a text file. So it's like an ASCII format file. So it's got no structure to it. You cannot query it like you would query an Oracle table. So when you can write a program, however, which will say, okay, I just want to extract column number 8 till column number 20, because I always have in that the ID of the user, right? So you could write a program which will say, okay, give me all the values starting from column 8 to column 20. And you would use at that time something like Java or Python or Ruby to do that part. And once your program is written that can do that part, you will submit it to the Hadoop system, which will then create an output for you, which will have all the values from column 8 to 20 for all the rows in your log file. So you'll be able to know all the users that logged in. That's the kind of things that you can do with Hadoop and using these languages and all. Right? Getting it somewhat? Don't worry. I mean, as we go forward, you learn more and more. It's a very different concept. Oh, okay. So some of the good features about Hadoop, why people like it. It's very fault tolerant. It's very highly scalable. It's very cost effective, and it's very flexible in deployment. It's very efficient. So what do we mean by these terms? You know what when we say fault tolerant, what do we mean? Any idea? Okay. Fault tolerance means something happens in your system which is a fault. Like, for example, let's say your hardware fails, right? Let's say if you had an Oracle database running on a Unix machine, and the Unix machine had a problem, and it went out of commission. It's not on the network anymore. All the users will be thrown out, right? You'll come to a grinding halt. Nothing can happen after that. Hadoop is fault tolerant. Even if the machine fails, the whole system will not collapse. It will allow the system to function. The user won't notice. Isn't that great? We'll see how it manages that, but that's one of its features. Highly scalable. So scalable means, you know what it means? It means that once you've defined its boundaries, you can still keep on expanding it. Scalable means that it's not that it has any fixed limitations in terms of how much data it can store, how many servers can you use on it. It's very scalable. It can grow linearly. It can grow to thousands of servers, thousands of nodes. You know, it can grow, contain data which can be a few terabytes to like gigabytes, zettabytes, and all that we saw earlier. So it can go to huge, immense proportions. It can scale up. This is something which is not possible in traditional databases like DB2 or Oracle or any other RDBMS. Okay. Cost effective is because it's all open source. There are companies which have started specializing in it, and they offer their own solutions for big data, and they do charge for it. However, it'll still be cheaper than the very expensive solutions provided by those big companies, IBM or Oracle and others, right? Flexible to deploy, it uses what is called as commodity hardware. You know what's a commodity hardware? Just like the laptops that you and I are using, this is commodity hardware. We can go to a local store and buy it. Right? So you can actually create a data warehouse or a huge data store using Hadoop, using just these kind of laptops. If you give me your laptop, Hetal, and I take yours, Mehak, and I put mine together, I can create a 3-node cluster in a Hadoop environment. Okay. Right? So I don't need to go for, those expensive servers, which cost like, hundreds of thousands of dollars. Mm-hmm. We could just use regular, day-to-day computers that we use normally. and we can tie them up together and start using them. That's what's happened with companies like Yahoo and all. They're using commodity servers to host. That way they can afford thousands of servers to work in parallel. And if one fails, it's okay. It was inexpensive anyway. They'll throw it out, and the rest of them continue to work. And their data doesn't get lost because Hadoop allows you to replicate data between different compute nodes, or computers. So those are the good things about Hadoop. Okay. It's efficient because it uses a lot of good features which we'll learn soon on all these different things like being fault tolerant, being able to handle huge quantities of data very quickly and efficiently. Now this, what we are covering today is more the architecture, what are the components, so you'll start getting an idea about Hadoop. You won't become an expert today, but you start to get a hang of, what's Hadoop all about. What kind of things does it use? So this is like explaining what are the different cluster components. Now, as Hadoop is evolving, it's naturally coming up with multiple versions, okay? So this structure that you're seeing here is more for what is called as a version 2.0, before version 2.2. After 2.2, Hadoop added a few more components, which we'll talk about later. But just to get you started so that you don't get too confused, it's a good idea to also look at how it started. A lot of people are still using this, although it's going forward with higher versions. So there's a component called Yarn, Y-A-R-N, which came out more recently after version 2.2. But before that, it didn't have that. So this one is a pre-2.2 version data diagram that explains, an architecture diagram. So you see on the top, there's something called a name node. There's something called a secondary name node, okay? And there are some data nodes. So as the name implies, so each one of these you can see is actually a different computer. It could be all combined into a single computer as well, right? If you wanted, you could do everything you want to do in Hadoop on a single machine. But typically, that's not the way people will work, because then you're not utilizing the full power of Hadoop. You might use it in a test environment or a development environment to just have a single node and just have everything in it. The name node, the data node, everything can reside in the same single machine. Because all of them are really nothing but separate daemons running on the machines, which are basically background processes. When you use Unix, Unix system works through processes, right? So all of these different nodes and all are essentially having separate processes running for them. So you see the one on the top is called the master, and all these data nodes are called slaves, right? So the master, the name node is the master, and the secondary name node is something that backs up the master. It can take over the position of the master if the master fails. So the secondary name node can become the main name node. So why do we have the secondary name node? Because if you look at this diagram, you see what happens is, one minute, what's written over here? This is a collection of, collection of data nodes. Now, typically, there's something also called a rack, just for your understanding. And a rack is actually a cluster, it's a collection of data nodes which are physically together and on the same network. So when all these different data nodes are on the same network and they are physically close together, they form a rack. Typically, there's something like 30 to 40 nodes can be there in a rack. Now, it's possible that in a Hadoop cluster, it's possible that these data nodes are not on the same network. They can actually be on different networks. One could be a server lying in Amazon Cloud. Another could be a server lying in a company's data center. So in that case, there are nodes which are spread out geographically and on different networks, right? But they could still be a part of the Hadoop system And the files that you access will be actually residing across different servers on different networks. It's possible to do it with Hadoop. Now that's something which will not be possible with traditional systems. Okay? So what happens here is this name node, we'll start learning more about this now. What kind of information does this contain? What kind of information is stored in these data nodes? This is something we'll see now. And these job tracker, task tracker, these are separate processes which are running on these specific nodes. And they are kicked off when you actually start Hadoop. Okay. So any questions so far?
No.
Okay. Now, we'll come back to that diagram and we are going to see what happens in a Hadoop HDFS. We need to understand that to be able to understand that diagram better. So, Hadoop is a distributed file system. We say that, files are stored in blocks. Actually, in any operating system, there would be some blocks, right? If you have a file which is on Unix or any system, even DOS, there are always blocks which store data. So one is the blocks which are contained in your operating system, and then there are blocks which HDFS uses, as you said earlier, Mehak. So it's Hadoop file system resides on top of the local file system. Okay? So when you start Hadoop on a server, then you actually get access to the Hadoop file systems. Otherwise, you're just sitting on your operating system with no access to what's contained within Hadoop. So now, when we say blocks in Hadoop, so what's the big advantage? Why should we have separate blocks for Hadoop versus what's already on the operating system? Why duplicate the whole effort, right? There's an advantage. Advantage being that although on the operating system you have smaller blocks usually, you have like 8 bytes or 16 or 32 bytes. In Hadoop, you actually have bigger size blocks. Like a block could be 64 megs. That's the default. Or it could be even larger. So you know what can happen, what it means? If one block is containing 64 megs of data, right? Then you can imagine that in about 20 blocks or so, you've already crossed 1 gig, right? So what this means is that, if your data becomes large, you could actually have files which are larger than the size of your computer's hard disk. Let's say if you had a computer hard disk of let's say 500 gigs. Your Hadoop file can actually 2 terabytes or something, which won't even fit on your computer. And the reason being that Hadoop will distribute that file on your computer and put the balance data on other computers. So that collectively, your data is now residing across multiple computers or nodes, right? So your file has been spread out to more than one physical machine. Got it? So that's the beauty of the system. So this is how it can handle huge amounts of data across smaller computers. And then it utilizes replication for fault tolerance, which means, what this means is your data is replicated, which means, let's say, if your resume is stored on one node, right? The exact same resume will also be stored on another node as a copy. The reason it does that is to become fault tolerant. So which means that one node dies, you should be able to get to the data from the other node. Okay? So when it writes files, when Hadoop writes information about blocks and files in its file system, it puts them not in just one node, it spreads them across multiple nodes. So every data block will actually be replicated to more than one data node. And you can set it, when you set up your configuration for Hadoop, you can specify how many replicated copies do you want. So if you mention a factor of 2...
So, but isn't it we are wasting, memory or something? Replicating data every time.
The reason is it's trying to minimize the risk of failure. So if what happens is, since you're using commodity servers, you're cutting down on the cost immensely. The chance increases now that your computer will die or fail or some hardware problems might occur, right? If you're using commodity servers, so something can happen, hard disk can crash, right? To avoid that risk, it allows you to spread your data across multiple nodes. And to be honest, storage capacity is getting cheaper every day. So today you can have 1 terabyte of data, which will not cost you as much as it would have costed you to get like 100 megs of data, like 5-7 years ago. So this is a negligible. What you're saying is right. It does mean that you need to have more space available to store your data, but it also brings you a big advantage of making sure your system doesn't go down no matter what happens. So you protect against those failures, and that's a big thing for, usually when companies put up large infrastructures, they have something called uptime and downtime. They measure the success of your system by saying how much is your uptime. So if you're, let's say, if you were on a data center and you had a server which kept running all year around, but it went down like maybe just for 3 days in the whole year, it brings your uptime percentage down to almost like 96% or so. So you were not 100% up for sure, but your figures start coming down rapidly. So when hardware vendors sell their hardware and they say what's their uptime and all, they tell the clients, our uptime is 99%. To be honest, 99% is also not a good uptime. It means that your servers can still fail, 2 or 3 times in a year. In Hadoop, that failure is immensely reduced. There's almost no chance unless you design your Hadoop cluster poorly. If you really care about keeping your systems up and running and you design it properly, you will never have a failure because the system went down. Right? Okay, next we go to this one. So we'll come back again to the same diagram I had shown you earlier to understand some more things better. So this is telling us like what are the different components of Hadoop, HDFS, Hadoop Distributed File System before the 2.2 version of Hadoop. We saw this already: name node, secondary name node, data node, job tracker, task tracker, right?
So which is the latest version you told?
The versions are going up every day. The last stable release that they had was 2.0.6. And then there was a version 2.0.7 that came out, but that's not announced as a stable release. They're still doing some bug fixing in it, so I won't install that if I were you. We would rather install 2.0.6. Okay. So this one, name node. So what's a name node? A name node, as we saw in the earlier diagram, let me go here. This is the one on the top. It's the master. It only stores, it doesn't store any data at all. There's no data in the name node. The only data that it stores is the data about the data in the other nodes, which means metadata. You know what's a metadata? You'll find this term as you go doing
data about data.
It's data about data, right? So what kind of metadata does the name node need to contain? It contains information about which block and which file is lying in which data node, right? So it kind of like keeps track of addresses of data across all the different nodes. Like I said, if your resume was lying in 2 different data nodes, let's say this was data node 1, data node 4, then the name node would know that kind of an information, like which data blocks, all the addresses of those, and which files have what data blocks, and on which node are they residing. So files, data blocks, and node information is all contained in the name node. Now here's something interesting. If you look at this feature. Now what happens in that case is this becomes a single point of failure, the name node. If this fails, you will suddenly lose all information about what was contained where. One of this data node might be on Amazon, the other one's in maybe Google, the third one's lying somewhere else. And now this node had all that information. And if this dies, we won't know where our data is lying and what's contained in there. Total loss. So although we say it's fault tolerant, here's one example of how it can mess up. So that's why they say when you design the system, although it's replicating with this secondary name node, it's not an online replication. The secondary name node just takes snapshots of the name node. So, at regular intervals, it will take a snapshot of the name node. So it will contain the same data as the name node has, but since it does that snapshots at some intervals, so if a crash happens, it can only go back to a certain point in time, but there will still be some loss of data. Right? So to protect against that issue about the name node dying, it's very important to make sure that the name node is a solid computer. This should not, as much as possible, be a very, old or, outdated system or something which is not sturdy. You need something really robust for having a name node. And since it contains information...
like server?
Yeah, it's like a server, yes. All of these actually... Huh?
Yeah, somewhat similar to server systems, right? And these data nodes will be acting as client systems.
Yeah, it's more like master-slave relations. So it's client. I'll explain the concept of client, which is also a separate concept. The clients will be people who are going to use or applications that are going to access this whole cluster. This entire thing is one Hadoop cluster. So anybody who's trying to access this Hadoop cluster would become a client. So if you had a big application or let's say Ruby or Python that wants to access this entire cluster, then that program that's accessing it is actually a client. Okay? So the name node is extremely important, and it also, since it contains information about every node and every single block and every single file, then this name node needs, and it also has this job tracker running on it, which is again kind of like a master for these task trackers running on the other nodes. So
if at some point of time, if we say name node crashes, and secondary name node will take its place. So the job tracker will be there also in secondary name node? Will job tracker be a part of it also later?
That's a good question. I don't know what will happen to the job tracker. It's a good question. I think the job tracker being a process will die down immediately. So what will happen is job tracker is nothing. So there will be data loss because whatever was happening at the point of the crash will be lost. So at that moment when the job tracker was running, when the crash happened, it was maintaining or monitoring these task trackers. Okay? The job tracker keeps information about which task is running and what is it doing. And job tracker decides who to assign the task. Like when a Python application comes in and says, okay, I want to run this certain data processing. It needs to analyze some file. Okay? The job tracker will decide whether to send that task that it has to create to this node or that node, right? So if the job tracker dies, now nobody knows which task was being handled. All of a sudden, we'll not know what all was running on all the different data nodes at the point of the crash.
Yeah.
So definitely the job tracker will not get alive when the secondary, and it's not seamless. What's happening is when the name node dies, the secondary node doesn't come online on its own. It's just taking snapshots. So it's just taking a picture or a snapshot of data as it existed at a certain point in time. So the secondary name node...
So that means we can only retrieve old data, not the current data, right?
Yeah. You will only be able to retrieve some old data, but not all the current data, right? So let's say if some file was being written, you were adding new resumes or some information, and the crash happened, and the name node had not yet replicated anything. Now it won't know where the resume went and was lying, right? It never got the chance to get that information. So there will be loss of that amount of data.
Yeah.
So this name node should really be a very sturdy system. It should have a large amount of memory also, because it's containing a lot of information about different things, different data which is stored inside all these data nodes. Okay. So it's very important to have this name node as a solid sturdy server. So you were talking about here about the name node. So this is what it's specifying. It contains metadata, about the blocks and all which are stored in other data nodes. It's backed up by the secondary name node. It's constantly updated by the data nodes, which means the data nodes actually keep sending information to it. What happens is, when so the question came up about the client. Let's say a client comes in, a Ruby program is accessing this cluster, and it starts writing data. When a Ruby program accesses this cluster, it doesn't have to go through the name node. The name node will initially tell it where to go, like which particular data nodes contain the resume you're asking for. From that point onwards, the client can directly go to these data nodes. It doesn't have to then keep informing the name node what it's doing. The task is started by the job tracker, and then the task is interacting directly with the client program, right? So the data node has to keep now if that task and actually writing data, right? Let's say it's creating data in the data node. Then the data node knows about the data, the name node doesn't. So the data node has to tell the name node, hey, look what, I got some extra data now. There's an extra resume. It's lying on so-and-so block. So, I'm just giving an example. Of course, it won't say something like that. But basically, it will tell it that, I created some extra blocks and there's data in it, and, these are the IDs of the data and all. Okay? So that's what's mentioned over here for the name node. It stores the entire file system, metadata, in memory. So it's very memory intensive. Now, the one other way to actually protect it is by using regular operating system, things like mirroring. You could have some extra software deployed, which will, whatever is happening on the job tracker, this name node, can automatically get replicated to another standby server. That way, if this one dies, you have no problem at all, because all of it is being instantly replicated to some other one as well. So you could use that kind of additional technology to protect yourself. Now with the post 2.2 version, there's some features available which bring in a better control on this kind of a failure of the name node, but we'll see it a little later. So this was about the name node. Secondary name node we already talked about, right? Data nodes. Now let's see the data nodes. How do they store data? You see here block 1 is on this data node, on this data node, and on this data node. So there are 3 nodes which are carrying this data. And these block 1s are actually the blocks of the Hadoop file system you created. So each one of these blocks could be like 128 megs in size. So across these 3 data nodes, you spread your data out. So if this node crashes, you still have block 1 in this one. No problem. So you'll be able to recover it. If this also crashes, no problem. You have this one, right? So your data loss is protected a lot. So you see over here, so block 2 is designed for every block. In this case, there are 5 blocks, and each block is lying on at least 3 machines.
So, for example, if
3 copies of every block will be maintained.
Yeah, correct. 3 copies of every block is maintained. Perfect, right?
Okay.
And it will never store the same block twice on the same machine. It will be across 2 different nodes, right? Across different nodes.
So my question was like, suppose if some client approaches Hadoop architecture, Hadoop system, to access some data or some analysis. So the name node will refer to some data node, right?
The name node will tell the client
Which data node?
Right, to go to, right.
Yeah, but here we have blocks on different data nodes. So which data node it will refer to? When we
Right.
have same blocks on different data nodes, right?
Yeah, the client will be transparent here. The client will not have to handle which particular data node to go to. That's handled transparently by the Hadoop system. So all the Java programs on which it's built, that handles it perfectly well. So basically the client will get the feeling that it's accessing a single file, but internally Hadoop is handling everything. So Hadoop will, suppose the client is went to block 1 and suddenly this machine crashed. The client won't even come to know that it kicked off, it changed that process, the process that was serving the client, let's say process P1. What Hadoop will do is, it will detect, that job tracker will detect that the task P1 failed. So job tracker, what it will do is, it will immediately start a P1 on this other node. The same, task or the process which was running will get started on this other node then. That's what.
So is it purely decided by name node, that which data node to refer first, and then how it changes the reference to the data nodes?
Yeah, the name node is simply kind of like a phone book or a directory that holds address information, right?
Yeah.
So now the job tracker is the one that starts the processes. Like a client approaches and needs information, or needs to write information or read information, then the job tracker will start a process which will start helping the client in getting that information. So, the job tracker would know, okay, this guy is asking for an I/O, like an input-output operation. He's asking for reading a file. All right, fine, I'll give him what he requires, and I let him take that file from node 1. All of a sudden what happens, node 1 crashes. And the job tracker comes to know immediately. It will say, oh, that one crashed. Not a problem. So it will slow down a little bit for this client. In the meantime, I'll kick off this other. It knows what's going on, what happened on that block and all, because the data node keeps sending that information of changes that's happening on it. So it will kick off the same P1 process that was serving the client. It will start that same process on, let's say, node 2, because that block is all.
So I think her question was that who will decide that node 1 has to be accessed first, or which node has to be accessed first for certain block?
Right, that's totally out of.
Yeah. So
we don't have control on that.
Is it sequential that the job tracker will always start from the node 1?
No, it will try to figure out. It does some computation. It has its own algorithm. It tries to find out how can I best serve this request. So it knows.
So there will be some mechanism for finding out the best node to retrieve the data.
Right. It knows what blocks are on which nodes and which ones are busy, which node is better to send to because it's more idle. So all those kind of that kind of monitoring and tracking is done by the job tracker.
Okay.
Right. So we don't have control over it. It's all internal built-in algorithms. So we don't monitor that. Yeah. But yeah, there would be some explanation as we go forward. We'll learn more. Like what logic does it follow generally to handle tasks?
Mm-hmm.
Yeah. So here's the job tracker. We already talked almost all about it. So it's typically a master node of the cluster. It's intermediary between the client and the cluster, like I said. So the client requests something from the job tracker. The job tracker starts the task tracker, and it assigns the task to it. And then the job tracker can cut off, and the client can access the task trackers directly. And it monitors the tasks and reassigns failed tasks. Okay. The task tracker, which is the final one in the loop, so it's again residing on the slaves. So a task tracker, usually one per slave node. Okay, so Just hold on 1 second. Okay, so what will happen is, a task tracker is one per slave node. So it handles the jobs which are assigned to it by the job tracker. Are you still there?
Yes.
Okay, good. Actually, I got interrupted by another phone call, so I'm sorry. I was wondering if you guys were still there, or I got cut off. So these task trackers, what they do is, there's something called JVMs, or Java Virtual Machines. So these JVM processes get started every time. That's what the task tracker deals with. For everything that it handles, for the tasks that it handles, in parallel, it uses JVMs. So the task tracker communicates with the job tracker and provides a heartbeat, which means it will keep sending the job tracker the information that it's alive, it's not dead, it's working, right? So it's called a heartbeat. And the job tracker spawns a new task tracker if it detects a failed one or a missed heartbeat. If it finds for a single instance that it didn't hear from the task tracker, it'll assume the task tracker is dead, it'll cut off, and it'll start the same process or another job tracker on another node. Okay. So this is how it is. So you have a name node, you have data nodes, you have job trackers and task trackers. And if you see over here, now comes another concept called map reduce. So there's a map and a reduce process running here from the task tracker. These map and reduce programs are nothing but these are programs that you write in your Ruby, Python, Java, and all other programming languages. And so those programs are run by the task tracker, right? And you see
So this map and reduce are two different things.
Yeah. So we will learn as we go forward that in Hadoop, it uses the map reduce system, and we'll see what it means. There are two separate steps. The data is first mapped, and then it's reduced. When you first do a mapping, and I don't want you to get too confused at this point, but essentially when you do a mapping, you start using a key value pair. All your data is actually converted into keys and values, one value for every key. So that's where your Python and all, where we've been talking about dictionaries and all, it will suddenly start becoming very interesting. So everything is a key value pair while mapping. And the key value pairs which are generated by the mapper are passed on to the reducer. And essentially the job of the reducer is then to aggregate all that data that the mapper produces. So you might have, just for an example, just very quickly I'll tell you, for example, let's say if you were having data or information about everybody who lives in America and their social security numbers, okay? Now, if you were to compile that information, that will be huge, right? Because there are millions of people living here. So what you would like to do is you might like to split it such that you have like maybe 20 files or maybe 50 files, one for every state of US. So what you could do is your data could be split up into 50 different tasks. So there would be 50 mappers running in parallel, each one processing the file for one state. So, so the social security numbers of every person need to be extracted, and maybe you need to sum them up to say how many people live in every state who have been registered with social security numbers. So you're summing them up. So the final sum will be produced by the reduce job, but initially, just to get hold of all the social security IDs from the file you submit, which might be buried in there from character 8 to character 20. So it will pick up, every single file will have that information, and it will be, picked up by the mapper. The record ID might be the key, and then the actual social security would be the value, right? So that will be 50 different states. Okay, did you get it? And then it will be passed on to the reducer. It's a little interesting feature. It's different from the way that files are processed, but it's a very interesting way of extracting information and aggregating data and using it for analytics and analysis.